Hey, welcome! Come on over! This is RoMeLa, the Robotics and Mechanism Laboratory, and this is where the magic happens. Come on in. You can see all the awards plaque that our students won, best paper awards, competition awards. We really started with autonomous vehicles. If you remember, way back in 2007, you probably remember the DARPA Urban Challenge. It was the grandest, the most challenging project at the time to develop fully autonomous cars. And we placed a third place in the world, and that really put us on the map. And since then, we started to move on to different things. This robot is called Charlie. It's considered the United States' very first full-size humanoid robot. Well, by the way, I have a lot of books, bestseller books. Also, the only non-rich person on the cover of Forbes magazine as well. Yep, very, very proud of our students. Oh, I'm also a gourmet chef. I don't know if you saw it, but I was on Master Chef Season 4 with a robot. But anyway, that's a different story. Come on over. So, if you've been to UCLA campus, we have the Luskin Conference Center and a 5-star hotel. This robot is called Lara, Luskin Automated Robotic Assistant. And this was actually used to be in the lobby, and this served as the concierge robot. As you can see, this concierge sign up here, so people can ask questions and Lara answer things. It's broken, so we had to fix it, but it's been here for, as you can see, quite a bit of time. I gotta work on that. But this is Charlie. Now, in robotics term, this is ancient. This is what? Oh, 12 years old already, but this is a historic piece. It's considered the United States' very first full-size robot, a bipedal humanoid robot, and it's fully autonomous. That we use for RoboCup. We're gonna talk more. So this is RoMeLa. This is where we build, do research, and do all these things. Yeah. By the way, it's not that clean, which is a good sign. If your lab is too clean, that means that the students are not doing their work, so this is good. We build a lot of robots. Of course, doing robotics research does not necessarily mean that you have to build robots, but we call these hands-on, minds-on learning. Minds-on, of course, you study and do all these things, but we all like to build things, break things, and test things, and that's a very important part of our research and education as well. You can see a lot of prototypes, building things. Yeah. Well, I think you're here to see our robots, so let's do that. Alright, so this is where we test our robots. As you can see, it looks like a soccer field. So yeah, this is one of the areas that we also test our robots for playing soccer for RoboCup. So let's talk about humanoid robots. Of course, we want to show you Artemis, which is, you're one of the very first people to see it in person or through the camera lens over here, or see it live. Humanoid robots are robots that look like human. 2 legs, torso, head, and 2 arms. You know, I have a dream in the future. I would like to have robots living with us, doing the dishes, taking out the trash. And I claim that the robot needs to be human shape and size to navigate this environment and use the tools designed for humans. Like, for example, look around. We have stairs, and those are designed for humans to walk up, or the door handle certain height for humans to open up. So unless the robots are humanoid robots, it won't be able to navigate this environment designed for humans. And that's why we're developing humanoid robots. Let me show you a humanoid robot called Darwin. Do you have Darwin ready? Yep. Yeah. Darwin stands for Dynamic Anthropomorphic Robot with Intelligence. This is a robot, you probably, if you're interested in robots, you've seen Darwin. It's one of the mostly widely used humanoid robots for research and education out there. I don't know, hundreds or even thousands of units are being used worldwide at, in the university and research labs. So yeah, let's try to do a quick demo.
Demonstration.
Okay.
Sensor calibration.
So let's put it on the ground. And take a look. So we are not remote controlling it. The robot is looking for the ball and tries to follow the ball and kick the ball. All right, there you go. Okay, you can do it. Kick the ball. Yay! You want to kick over if you want to? No? There you go. So you can see it's following the ball. Let's do it again. You can do it. Darn it, you can do it. Kick the ball to the goal. No dribble? Okay, that's fine. Yay! So this is Darwin. So we made Darwin completely open source, which means that all the software or the hardware, the CAD files, where to buy parts, how to fabricate the parts, how to assemble it, everything is online for free because we want to make this accessible for research and education. So this is one of the most widely used robots in the world, humanoid robots. And also, So if you go to, the reason why we're doing this is because it's for research and education. If you go to international robotics conferences, so many new knowledge and papers and theses are being built, and new robots are being built based on Darwin. So among the many impressive robots, I think this robot had the biggest impact to the robotics community. So this is Darwin OP. Thank you, Carl. So yeah, Darwin OP is great. It's fun. It's actually not, it's not a toy. It's actually kind of expensive. But smaller humanoid robots, yeah, we had success of making it walk and do things. But to make these robots do really useful stuff, it needs to be big human size. But these robots are very difficult to scale up. But we tried. So one of the big full-size robots that we built is Thor. RD. Thor stands for Tactical Hazardous Operations Robot. RD stands for Rapid Deployment. So this is one of the robots in the Thor series robots that we built. As you can see, it's a human-sized humanoid robot. And this one was really developed for disaster relief applications. You probably remember in Japan a long time ago, the Fukushima Daiichi nuclear power plant accident. It was a horrible accident. It's still a very big problem, but because of the radiation, people cannot go in. So this is where we use robots. So this robot can drive a car, climb upstairs, open a door, open and close valves. So it's really designed for rescuing people and for disaster relief. So yeah, so this was a very successful robot, but still that was, what, 10 years ago already. So this is also an ancient robot in that sense. Unfortunately, we're not going to run it today, but still it's a very valuable research platform. So unfortunately, we won't be able to run it today, but if you see some of the videos of Thor walking, they walk like a robot. They're chunky, they're slow, and they can walk on smooth, hard, even terrain. But if you bring it outside on the unstructured environments, it always falls down. One of the main reasons is because these actuators. Now, when you say actuators, you're talking about devices that make the robot move, like muscles and biological organisms. Now, these type of actuators, or as a matter of fact, most of the actuators that exist today, electrically driven robots, use servo motors, which means that we have an electric motor with a huge gearbox. Now, you might know that electric motors, the output is really fast but very weak. So by having a 1 to 300, 1 to 200 gear reduction ratio, we can increase the torque, or make it strong and make it slow it down so it's usable. We call these servo actuators, and we do position control, and that's why robots move like a robot, right? So using these type of actuators, they're really great for factory automation. As a matter of fact, you probably know that your car was built using these type of industrial robots. They're precise, they're rigid, and they're very accurate. Great for manufacturing, but they're horrible for walking or running or trying to use these type of robots in the unstructured real-life applications. We need something different. We need something that's compliant or springiness, and not only the position, but something that can also change the force, like a biological actuator. I'm going to talk about that in a minute, but let's take a look at some other robots first. Now, why are these robots constantly falling down? Yeah, actuator is one big problem, but I tried to ponder this question. Why fundamentally, why is this so difficult? And we found something really interesting. Now, one of the reasons why these robots constantly fall down is because the distance between your left and right leg. This distance is actually a problem. Why is that? Because your leg moves forward, backwards, up and down. And because of distance, leg moving, it creates this unwanted twisting moment. And that's why it falls down. I was watching TV, fencing, or ballet. They always walk sideways, because when you walk sideways, your left and right leg line up and all the twisting moments disappear. Voila! All the problems solved. From now on, all the humanoid robots are going to be walking sideways. That's kind of weird, right? One of the problem is not only it looks weird, but you cannot really use your knees. So what do we want to do? We want to switch our knees like this. That's awkward. Let's actually change the lower body like this. Okay, now this makes sense. And thus we build a new robot called Nabi. Nabi stands for non-anthropomorphic biped. In other words, it's a robot with 2 legs, but it does not look like a human. And it walks like this. So instead of a left and right leg, it has a forward and backward leg, and it walks like that, right? And it's stable, it's low cost, it's fast, it's safe. So just by that very, very small change from this to this, we solved most all the problems of bipedal locomotion. Isn't that great? By the way, there's a reason why we use this cheap cardboard box, because we want people to, when you see this, because it's a cardboard box, you know, intuitively you know that this is not an expensive robot, and that was intentional. And you see this very cute face, which is now the signature look. There's a reason why I put this on. When we did not have the face, people thought it was a sideway walking robot. So, oh no, this is forward. We just put a face and all the problems solved. So this is Navi, non-anthropomorphic biped. So this was a huge hit. It was a sensational new type of approach, literally thinking out of the box for bipedal locomotion. However, it walks forward and backward brilliantly. How does it change direction? It can't. If you hit it forward and backward, it can balance itself. But if you hit sideways, it's gonna fall down. Doesn't mean that this is useless. Not really. It's a feasibility study of a new type of bipedal locomotion robot. So now let's try to make it more useful. So think of two Navi robots, but we stack them on top of each other. And that is Alfred. Okay, this is Alfred. Unfortunately, we're not gonna run it today. So you see these four limbs. We don't call these legs. We don't call these arms, we call this limbs, because you can use it for legs when walking, but you can also use that arms for manipulation. For example, it has a very wide stance, which is great for unstructured environment. But if you want to make it go faster, you go like this and this. Now you have a four legs and backward legs, and you can make it gallop and run. Or you remember Navi, right? So when it walks with two legs, the other two legs, you can use it for picking up boxes or pushing up buttons. And we're now doing some research, trying to make it do cartwheel as well. So we call these multimodal locomotion, trying to make it move in many different ways. And that is Alfred. Now, let's go back to the actuators. We talked about these position control servos. They are stiff, and we do position control, but what we really need is compliant springiness, and also not only the position, but also change the force. Thus, we developed a new type of actuator called the BEAR actuator. BEAR stands for back-drivable electromechanical actuator for robots. And what you see over here is, remember Navi, the two-leg robot? This is a version of Navi, but it uses the BEAR actuators. Are we going to run this today? No, not today? Okay. So you can see that unlike other robots, it's back-drivable. And this, again, I'll be happy to share with you videos, but this can jump, hop, run, walk with two legs, and now it's more biological motion, so this was a breakthrough. So the BEAR actuator with Navi together is Navi 2. Then the BEAR actuator with the Alfred, that is Alfred 2. Can we run Alfred 2 today?
Yeah.
Okay, so when you look at it, it's very smooth. When you see it's more natural, organic, if I may say. So again, it's omnidirectional, there's no forward and backward, but if you want to make it go fast, then you can change your configuration. Now it can run. Now we don't have a lot of space here, so it's not going to really run. Run for your lives! I was kidding. But this robot can walk, jump, hop, walk with 2 feet, and you can use the other 2 limbs for picking up boxes, knocking on doors. We also did some demonstrations of breaking boards like Taekwondo, right? And this can walk and run outdoors in the unstructured environments as well. Yeah. Good robot. Cool, I think you're done now. Okay, you can rest now. Alfred 2, go back to your home. Good. So we talked about why we need humanoid robots. We want to have robots living with us. It needs to have the human shape and size. But because we had difficulty with bipedal locomotion, we had different weird configurations, and then suddenly we have 2 legs to 4 legs and even different things. Why not 6 legs, you might ask? 6 legs, if you look around, insects have 6 legs. We do have a couple of 6-leg robots, but let me show you a robot called Sylvia. Help me out here. Sylvia stands for 6-leg vehicle with intelligent articulation. There you go. So it's a 6-leg hexapod robot. If you're into robotics, you probably have seen other hexapod robots, but this is a little bit different. This is the world's strongest hexapod robot, if I understand. It likes to dance too, like, yeah. But this robot is the world's very first robot that can brace between walls and climb up vertical wall surfaces. All right, but we're not going to demonstrate that today. Okay. We also sometimes use it for our students' birthday parties. It carries a birthday cake. It's a party robot. Yeah, but yeah, this is one of the very first robots that can do vertical locomotion, vertical climbing by bracing between walls. All right, cool. So this is Sylvia. So now we're interested in not only walking on ground, but also climbing up, like cliffs, or like, for example, we have a bridge, we need to do inspection tasks. Robotics, we call this a 3D. Dull, dirty, dangerous. Dull, things that we don't want to do, dirty work or dangerous work that people should not probably do, or things that we don't want to do. We want to have robots do it. So inspection tasks for these like big structures. Let's make climbing robots. So this robot is scalar. Also, we have not publicly shown this just yet, but we make this climb upside down vertical walls and things like that. It's not working right now. Well, we're doing testing right now, but this is a very exciting robot called Scalar. All right, so if you think about it, I talked about why we need humanoid robots and the difficulty that we have. So from humanoid robot, cause it falls down, let's change the configuration. So we have Nabi, we need different type of actuators, put the bear actuator, and we have this. And now we're diverging from the humanoid form. So let's go back to the original question. I explained why we need humanoid robots, but we had problems. Is there a way to make a bipedal robot low cost, safe, not fall down, and solve all the problems of other type of bipedal locomotion? We have built a robot that does this, and this one is called Balu. Is Balu ready? No, not ready? Okay, not ready, which is fine. Going back to the humanoid robots, do we have Bruce ready, you think? Okay, this is the very first time we're showing it to the general public. The bear actuator, the humanoid robot, Darwin. We have the next generation called Bruce. Bruce stands for what? Help me out, guys. Bruce stands for?
Bipedal robot unit with compliance.
Compliance, there you go. So you remember the cute robot Darwin, which was a huge sensation. It was a great hit. That's old technology, so we researchers need the next generation robot, humanoid robot, and this is Bruce. Again, it might not work. Let's see if we can do it. This is the very first time it's going to be on camera. So again, you guys are one of the very first people to see the Bruce in action. Where's Darwin?
Oh,
right here. Yeah.
Boot up. 3, 2, 1.
So again, 12 years ago versus 2023.
Start estimation. Ready? 3, 2, 1.
Okay, first time on camera.
Low level control. High level. Top level.
By the way, this also uses liquid cooling. You see these tubes. We pipe liquid to cool down the actuators too. What?
It's not balancing. Can you run the balancing again?
Okay.
Again, robotics is hard. So these type of robots, these are not like home appliances where you can just turn it on. So just to show you a lab tour and the live demo, the students stayed up all night and worked many days to set this up. So. And we're very excited to show you Bruce for the very first time. And this is Bruce. Say hi, Bruce. There you go. Hello, everybody. Welcome to RoMeLa. And it walks, it runs, it can jump. Let's go very slow today. So as you can see, the motion is very different from Darwin or the other position-controlled servo-based bipedal robots. This robot can run and it can jump. It can also do a backflip. However, it can jump and do a flip, but it cannot land just yet. We're working on that right now. But as you can see, it's a very different type of locomotion. And still, it's a work in progress. But the exciting thing is, just like we opened up Darwin as an open source platform that has a huge impact, we're planning to also do open source on Bruce. So researchers and students can use the next generation technology for doing research and studying. And we're very excited about this new robot, Bruce. Okay, now, humanoid robots. Big robots that can actually use in real life. They're slow, they're dangerous, they're expensive, they always fall down. Can we solve this problem? Yes, we can. We build a adult-sized bipedal robot that is the world's safest, low cost, and it cannot fall down. And that robot is Balu, and we have Balu over here. You want to push it over here? Okay. Just, yeah. And this is Balu. And Balu is a robot where the body is a helium balloon. It's ridiculous. It's a balloon with 2 legs. But it can walk, it can jump, it can hop, it can dance. And it's very cute. And it's also very huggable, right? And it's... So this is the world's safest bipedal robot because it doesn't fall down. A baby can crawl in front of it, absolutely no problem, right? And it's ultra low cost. So it solves all the problems that we talked about on humanoid robots. However, it also creates new type of problems. For example, this robot is horrible outdoors because when the wind blows, it floats away. Alright. So very cute robot. And that's Balu.
It's kind of like Baymax from Big Hero 6.
Yeah. So this is a similar concept in terms of safety. And it's not using hard metal things, but rather it's squishy, like a balloon. So it's really, really safe. So you can imagine, you probably, having these big humanoid robots walking among people, still very dangerous. But something like this, in an amusement park, right? There's kids around. This can walk between the kids and interact. How cool would that be? So this is Balu. There you go. All right, so still it has problems, right? It solves a lot of problems, it creates a lot of problems. As I mentioned, it's horrible outdoors. Or if we want robots to do useful work, if I asked Bolo to, hey, fetch me a can of soda, when it grabs it, it's too heavy for it because the buoyancy is limited. So is there a way to solve these kind of problems? I am very excited to show you our latest and greatest robot cart, Artemis. And again, you will be seeing Artemis live here. And this is Artemis. Yeah. It's completely untethered, walking with 2 feet. Now, normally it's autonomous, but for this demo, we're actually remote controlling it. And this is a first of its kind and the only of its kind. Everything is electric powered. And you remember that bear actuator that I talked about? I like to explain it as artificial muscles. And it's using those bear actuators. This is the very big version. Now I have to get permission from my students. Can I push it and pull it? Okay. You do not see people do this with these type of humanoid robots. I'm pulling it. I'm gonna push it. I'm going to bump into it. You do not see people do this with these type of robots. Alright. Come here. I'm pulling it. Now sometimes I kick it, but I'm not going to do it today. So it's really, really stable. So when it's we're doing some experiments, once we make it go on rubble pile, we couldn't make it fall down. We tried to kick it, shove things, throw balls at it, and we couldn't make it fall down. Right? Grab hand and got it. Let's go back home, come back home. Okay. Okay, turn around. Okay. All right. Thank you very much, guys. Thank you, Artemis.
Stop and go up. 3, 4, 5.
All right. So let me talk about some of the details of this robot. So again, it's a humanoid robot, 2 legs, torso, 2 hands, 2 arms, and a head. By the way, notice that it doesn't have hands yet because currently we're focusing on the locomotion part. Once that's all done, then next step is to have hands and make it do manipulation. Oh, by the way, even at this point, this robot can pick up boxes, move big boxes, push carts, so it's still useful. But at this point, as you know, we're preparing this robot for a RoboCup, the International Autonomous Robot Soccer Competition. It's a competition where teams from all around the world come and bring their latest, greatest technology on robots. It's a soccer competition where the robots play soccer against each other. Not remote control, but fully autonomous. The robots looks around, searches for the ball, kick the ball, and they play soccer against each other. We were 5-time world champions, but that was 8 years ago. So the last award ceremony. So in these kind of competitions, if you win once, people say, oh, that's because you had good luck. But we won 5 times, so everyone knows that we're the best. So at the award ceremony, we announced to the people saying that now we want to give other teams the opportunity to win, so we're not going to come to RoboCup anymore until in the future when you have brand new technology that your jaw is going to drop. Then we'll come back to RoboCup, and that's this year, RoboCup 2023. It's going to be held in Bordeaux, France, and we're bringing Artemis to RoboCup, and we cannot be more excited. So as you can see, it has two cameras, a stereo vision, so it looks around, searches for the ball. Because you have two cameras, you can get the 3D image from it, 3D information from it. Let's see, in here you see that small box, that's called an IMU, Initial Measurement Unit. It's like your balance sensor in your inner ear. All of the joints uses that bear actuator, so not only the position, but it can also sense its forces or torques, if I may say, using current sensing. We have some special technologies for the foot sensing as well. And yeah, this is it. Can you make it, let's lift it, I want to show the back.
No, it's not turned off. Wait.
Okay, just again, yeah.
Powering it off.
Okay.
2.
Okay, we're gonna power it off. Let's lift it up a little bit. Oh, by the way, every single component in this robot, except for the computer, wires, bolts and nuts, and the camera, everything in-house design and in-house built. All the links, everything, all the electronics, even the batteries, we custom build everything. Let me actually show you the batteries. Now, yeah. Okay, these are the batteries over here. I have 4 batteries. One is for the perception and computing. This one is for the upper body. This one is for the lower body, and this one is for future use. Now, this robot, at least the hardware, is designed for doing real dynamic motion. This robot can run, jump, do flips, and even do parkour. Now, we still have a long time to get there, but it's designed to do that. So when we're doing really dynamic motion, that's when we're going to be using this. And everything is hot swappable. By the way, which among the 3 batteries, which battery do you think is going to depletes first? Is it the camera and the computer, or the upper body, or the lower body?
Lower body.
Lower body, yeah, people think it's the lower body. That's what we thought too, but it turns out it's the first battery that handles the perception and computing. It uses a lot of brain power. So yeah, so this is the battery over here, right? So Artemis battery, even the battery that we design everything. So yeah, can you show the e-stop switch? Yeah. This, even the e-stop, emergency stop switch, this is the world's best and the only of its kind e-stop switch. We search for components on different type of products around the world. Nobody has something like this, so this, even the e-stop switch is pretty cool.
Dr. Hong,
Yeah.
how do you plan to fly Artemis out to Bordeaux, France for RoboCup?
Yeah, so good question. So RoboCup this year is going to be in Bordeaux, France in early July, and of course we need to bring our Artemis robots and students. So how do we travel with this? Very good question. So when we start designing the robot, because we are travel savvy, we do all these demos all around the world, so we start with these Pelican cases. You probably know these special cases for equipment. So we know all the standard size of Pelican cases. So we decide, okay, for this robot, we're gonna put it in 2 cases. So here, there's 6 bolts. If you undo 6 bolts, the upper body and lower body separates. The upper body goes into one case, and the lower body fits in another case. But another problem is batteries. You probably know that there's a limit to the watt-hour capacity batteries that you can travel on flights. I think it's 100 watt-hours. So what we did is we built 99 watt-hour batteries and 4 of them, right? So these are the special batteries, which are hot swappable, and that's how we travel with our robot. Yeah, so this is cool. Again, as I mentioned, this is designed to do very dynamic motion. For those who are actually on UCLA campus, you've probably seen Artemis already walking around campus. So every 2 weeks or so, we make it walk outdoors just to greet and meet other students. And also we're doing soccer practice on the IM field right now. So Sundays and Mondays, it depends, but we do soccer practice with Artemis. And of course, for the competition, we need more than 1 robot. And thanks to your generous support throughout the Spark campaign, we started to build the second Artemis. And let me give you a sneak peek of the second Artemis. And these are some of the parts which I'm showing for the very first time. Now, I consider this sexy. Look at that. If you're an engineer, you're probably drooling over this. This is the thigh link, right? So this is the one that goes over here. You see that? It goes over here. That's the thigh link. And these are the housing for the hip. It's like a piece of art. As I mentioned, one more time, every single component we design in-house, and we fabricate everything at RoMeLa. Right. So by the way, this is also, we're using some new technology. For those engineers, design engineers, probably heard about topology optimization. Some people call it AI design, which, you know, I don't like that term, but so we let the computer design the link for you. So for example, we give, oh, this is the volume that this needs to fit in, and these are some of the constraints of the position of the joints, and we tell the computer what are the loading conditions. And the computer does runs algorithms to come up with the best optimal solution. And we work with the computer to come with a solution, and this is the one that is spit out. And look at this, that's why it looks organic. Like if I had to design it from scratch, or some of our students, humans probably won't design something like this, but this turns out to be the lightest yet strongest against the loading condition that we specify. So isn't that cool? So these are parts for the second Artemis that we're going to bring to RoboCup 2023. So thank you very much for your support. Yeah. So Artemis, the name is also an acronym. It stands for Advanced Robotics Technology with Enhanced Mobility and Improved Stability, Artemis. But in-house in our lab, we call it a different acronym because, you know, it's going to RoboCup for robot soccer. So Artemis for us stands for a robot that exceeds Messi in soccer, Artemis. All right, I hope you enjoyed the tour of RoMeLa, the Robotics and Mechanism Laboratory. And don't forget to cheer for us for RoboCup 2023 this July, early July in Bordeaux, France. All right. Thanks, guys.